Hello, this is Dr. Joseph, and we're going to learn about parametric curves today. Um, so usually in pre-calc and calc, we're thinking of y being a function of x, or sometimes x is a function of y. Now we're going to think of points in the plane. So they have two coordinates, x and y, as depending on an independent variable t, which we'll often think of as time. And it's good to think of this as the path or trajectory of some object, and then at time t. So let's see a couple examples. Suppose that Sarah walks along this green path in the xy plane, and it's part of this parabola, y equals 0.1 x squared. So at any time t, it says her x coordinate is 2t. What is her y coordinate in terms of t? How long does it take her to walk the full path? Um, okay, so the path drawn here looks like it has x's going between 0 and 5. That is not time, right? Time is t. So that's just x coordinates. Um, and let's see. If y is 0.1 x squared and x as a function of t is 2 times t, y is 0.1 x squared. So then that's 0.1 times 2t squared, which is 0.1 times 4t squared, which is 0.4 t squared. So y as a function of t is 0.4 t squared. And it looks like let's get into Desmos for a second. And make a new graph. Okay, so the way you can graph something like this in Desmos is you put x of t and y of t into an ordered pair. So x of t was 2t and y of t was 0.4 t squared. And now this is graphing the parametric curve, and you can increase the domain for time t if you want. Um, and what's very cool is if you copy this again, replace all the t's with the same letter and add a slider, you can now move this around. And so when t is -2, these are the exact coordinates of this point particle. Um, so we could figure this out by plugging in and looking at what values we get, but there's a little bit faster to see at time 0, we're at the origin. And then we wanted to know at what time do we get to 5. And it looks like that's going to be at exactly time 2.5. Um, so hitting play, you get to watch the particle move, and this is just a lot of fun. So I'm going to do this a couple of times. Oh, whoa. Back to the iPad. So all in all, x of t, y of t as a ordered pair is 2t 0.4t squared. So when x is equal to 5, right, that's 2 times t. That tells us t is 5 halves or 2.5, as we saw in Desmos. Okay, so next, oh yeah, and this question, how long does it take her to walk the full path? Well, at time 0, she's at 0, 0, the origin. At time 2.5, she's at the final point there. So it takes 2.5. That's the question we just answered. It takes 2.5 seconds or whatever the unit of time would be. I'll just put seconds. Usually that's what we'll use. Okay, suppose that Ani also walks along the green path shown, which is part of the graph of y equals 0.1x squared. Okay, same as before, but now at any time, Ani's coordinate is square root of t. So that's the y coordinate. And then what is the x coordinate? So if y of t is equal to square root of t, we also know y is 0.1x squared. And our goal right now is to solve for x as a function of t. Okay, so coming back to here, 0.1 is 1/10, so that means x squared equals 10 square root 2. And then I could take a square root square root of 10 square root t. And it looks like x is positive, so I don't have to worry about the negative square root. I wanted the positive square root. And then that looks kind of weird, so let's just write it like this. Square root of 10 times fourth root of t is your x coordinate at time t. So the full parametrized curve would be root 10 times fourth root of t in the x coordinate and square root of t in the y coordinate. And oh, let's check this out. All right, so it's the same path as before, but a different parametrization. And so that means, so I'm entering t to the 1/4. Oh, oh, that's funny. I shouldn't use t. I should use a different letter. Um, because I'm going to have a y too, and it thinks t should be the variable when it's getting x and y coordinates like this. Oops. C. Okay. All right. So that's my parameterization now. And they're both from -10 to 10. And I want to play one and then play the other. Very different, right? You're getting a different set of points. You're a different part of the curve. And even if it had been the exact same path, it may have been at very different speeds, right? So although these curves are all lying on this same parabola, they're different parametrized curves. They're going through different parts of it and at different speeds. So there's a lot of information in this way of doing things. All right, back to the tablet. Bear with me. And the question again, how long does it take him to walk the full path? So again, this ends when x is 5. And we solved for x, and we said x was square root of 10 times fourth root of t. Whew, okay, so that means 5 divided by the square root of 10 is equal to the fourth root of the time where we reach an x coordinate of 5. And now I have to raise both sides of this to the fourth. So this would be 5 to the fourth divided by square root 10 to the fourth, right? And raising to the fourth is squaring and squaring again. So that's 5 to the fourth over 10 squared, which is 100. Anybody know what that is? That is 6.25 units of time. So different than the answer we had before, as you probably expected. All right, moving on. We also may want to go backwards. So starting with your parametric equations, x of t and y of t for a given curve, we may want to go backwards and find y as a function of x, or an equation that has x's and y's in it and no more t's, right? To know like what sort of shape the curve lies on. And this is a little bit ad hoc, as you'll see in the examples, but we basically substitute, and sometimes we use the Pythagorean identity. So first, in this first example, we want an equation. And looking at this first equation, it's very easy to solve and say that t is x minus 5, right? And then since I have y as a function of t, it's going to be very easy to finish this out, right? Because y is 3 times t squared. T is x minus 5. So I get y equals 3x minus 5 squared, and I'm done. And that shows me right there that it's going to be on a parabola. Okay, so this one, x has some function involving cosine of 4t, y has some function involving sine of 4t. This is where that Pythagorean identity cosine squared theta plus sine squared theta equals 1 is going to be helpful. And that's actually my strategy, is to solve for cosine theta, or cosine 4t in this case, solve for sine of 4t and plug them into this equation, and that will be the answer. So let's see how to do that. X divided by 2 is cosine of 4t. Y minus 1 is sine of 4t. And theta can be anything, right? As long as both the thetas are the same. So if I'm doing theta is 4t, this is a true equation, right? So cosine squared of 4t is x over 2 squared. And sine of 4t is y minus 1. Square that too. And this is it, actually, that we're done. So if you go into Desmos and graph this, you'll find that it is the graph of an ellipse. That 2 stretches the x direction by a factor of 2, and the plus 1 shifts the center up to the point 0, 1 instead of 0, 0. So it can be kind of easier to draw a lot of curves parametrically, but this is really the key to going backwards and finding an equation with x's and y's. All right. And here's a try it yourself. Given that x equals 3 e to the t plus 1 and y equals e to the t plus 1 minus 5, find the equation that relates y to x. So when you finish this, you'll see that the answer is a linear equation, even though our parameterizations involve exponential functions. And again, if you graph it with the slider in Desmos, you'll see that although the graph is a line, we're not moving at a constant rate. It is starting kind of slow and then accelerating as t increases. So that's all for this video, and see you next time.